This lesson's going to be on linear programming, and specifically, we're going to discuss how to do that graphically. So I want to give you some background on linear programming. First of all, linear programming is used by 85% of our Fortune 500 firms. And linear programming problems contain multiple inequalities. These inequalities are going to act as restraints. And so if you recall, with inequalities, you actually shaded different sides of the line. So imagine that shading overlapping and having this shaded region. The objective function is the function that you want to optimize. So you're going to be given a couple of things in these problems. You're going to be given an objective function that has an equal sign with it, and then you're going to be given inequalities that are going to serve as your restraints. Any point in the region that's determined by the constraints, which means you've graphed your inequalities, you've figured out where the shading has overlapped. That overlap shading is going to be the feasible region. And the feasible region is just that region itself, where all that shading overlaps. Where are the solutions going to be? Well, you can see here that there's a breakdown of 4 possibilities with solutions when it comes to linear programming. I want you to go ahead and hit pause, and I want you to read through these yourself. There's no need for me to read them out loud to you. But you can see, depending on whether the feasible region is closed, whether it's bounded, whether it's not closed and bounded, different things can happen. That being said, the easiest way to really understand linear programming problems is to actually do one. So let's go ahead and look at this problem that says find the max and min value of c equals 5x plus 3y, and it has the following constraints: that x plus y is less than or equal to 5, that 2x plus y is less than or equal to 8, and that x and y are both greater than or equal to 0. So up here is our objective function. Okay, it's got the equal sign. And then over here are our restraints. So what we're going to do is we're going to go ahead and graph the restraints. So you can see that I've taken those 4 restraints from the previous slide, and I've gone ahead, and for the ones that needed to be solved for y, I've gone ahead and done that. So I'm going to graph y is less than or equal to negative x plus 5. So 5 is our y-intercept. Slope being negative 1, we're going to count down 1 and to the right 1. I'm going to connect those with a solid line, and I'm going to check the point 0, 0. Is 0 less than or equal to 5? It is, so that becomes the shaded region for the first one. Then we've got y is less than or equal to negative 2x plus 8. So 8 is the intercept. And then we're going to count down 2 and to the right 1. And we're going to go ahead and put our line through. And we'll check the point 0, 0 again, and 0 is less than or equal to 8. So we'll go ahead and shade. And we want where x is greater than or equal to 0, so that's above the x-axis. So that's going to be here. And we want where y is greater than or equal to 0, so then we're looking to the right of the y-axis. And so we're looking at this region in here as our feasible region. So you can see that I went ahead and created the same graph using some graphing software just to make it a little bit easier to see. So I think with this one it's pretty easy to see where our region is located. So I'm just going to outline it in black. It's going to come down here, down to here, and over. So that's our feasible region. So in terms of the points that we're interested in, we're interested in the boundary points of that feasible region. So I'm going to go ahead and mark them in black. That point, that point, that point, and this point here. Some of those points are easy to see. So I can see I've got the point 0, 5, I've got the point 0, 0, I've got the point 4, 0. The one that I'm going to have to figure out is this point here, and I've got to determine where those two lines intersect. Again, if I have a graphing calculator, I can do that by tracing it and figuring out the point of intersection, but we can certainly also do that by hand. The two inequalities that we're trying to figure out where they intersect are the first two. So let's set them equal to each other and figure out where they intersect. So we're going to set negative x plus 5 equal to negative 2x plus 8. And we're going to add 2x to both sides, and then subtract the 5, which gives us 3. So we know that the intersection here happens at the point 3 something. So we can plug 3 back into either of those equations and figure out that that intersection point is at 3, 2. Your next step is to plug each of those boundary points in to that equation, that initial function, and determine which ones gives you max and mins. So you're going to take each of those values and plug it in to c equals 5x plus 3y, plugging in for x and plugging in for y, and determining the values of c. So when we go ahead and do that, we can see the values that we get running along the side here. So clearly our minimum happens at the point 0, 0, and our maximum happens at the point 3, 2. So we've got Smoker Meat Packing Company that makes two different types of hot dogs, regular and all beef. Each pound of all beef hot dogs requires 8/10 of a pound of beef and 2/10 pounds of spices, and each pound of regular hot dogs requires 3/10 pound of beef and 2/10 pound of spices, with the remainder being non-beef meat products. The company has at most 1,020 pounds of beef and has at most 500 pounds of spices available for hot dogs. If the profit is 90 cents on each pound of all beef hot dogs and $1.20 on each pound of regular hot dogs, how many of each type should be produced to maximize the profit? So we have to go ahead and figure out the profit function and then the constraints that go with it. So the profit function is located right here in this sentence. So we know that the profit is going to be 90 hundredths x plus $1.20 times y, where x is the number of pounds of all beef and y is the number of pounds of regular. Then we have to go ahead and get our constraints from this. So we know that 8/10 times x plus 3/10 times y has to be at most, which is less than or equal to 1,020 pounds. We also know that 2/10 x plus 2/10 y is going to be at most 500 pounds. And we also know that we at least need more than 0 of each of those things. So I want to look at inequality 1 and inequality 2. And what I've done in the work down below for inequality 1 and 2 is I went ahead in the first step that I'm marking there in blue and got rid of the decimals. So I multiplied every single thing by 10. That way I'm not dealing with decimals anymore. Go ahead through and solve for y for each of those, and we end up with one inequality that's y is less than or equal to negative 8/3 x plus 3,400, and another that's y is less than or equal to negative x plus 2,500. Let's talk about where these inequalities all intersect. So we've got some points again. Here is our feasible region, with those as our boundary points. So we've got the point 0, 2,500. We have the point 0, 0. We have the point 1,275, 0, which we'll talk about how to get that. And then the point of intersection that you see is 540, 1960, which we're also going to talk about how we got. So I think these first two you can see straight from the graph. How did we know that this happened at 1,275, 0? Well, we can see that it's the x-intercept of that red line right there. And that inequality that we see is the y is less than or equal to negative 8/3 x plus 3,400. So we need to figure out, when is y 0? So we can go ahead and solve for that by subtracting the 3,400 from both sides and multiplying both sides by negative 3/8. And when you do that, you're going to get that x is 1,275. The second point down here we need to determine because it's where this red and green line are intersecting. So it's where negative 8/3 x plus 3,400 is equal to negative x plus 2,500. So we can go through and solve that, and you'll get that x is equal to 540. You can take that 540, and again, you can plug it back in to either the left equation or the right equation, and you'll get that y is 1960. So that's where those 4 points are coming from. We need to take those points and plug them back into the function. So we're going to take each of those points and plug them into our profit function that we had found at the beginning of the problem. When we plug in 0, 2,500 for x and y, you'll get 3,000. When you plug in 0 and 0, you're going to end up with 0. When you plug in 1,275 and 0, you'll end up with 1,147 and 50 cents. And lastly, when you plug in the 549.60, you'll end up with 2,838. So clearly, this indicates that the profit is going to be maximized if 2,500 pounds of regular hot dogs and no all-beef hot dogs are produced, because that 3,000 is the largest of those four numbers. Let's do another where we're figuring out where the max and the min are. So we have our function f equals 4x plus 9y, and for the constraints below you have to solve each of those for y. So here we have a graph of that feasible region. So you can see again that we've got some points that we're interested in. We've got this one, this one, this one, and this one over here. So we need to figure out what those points are. The top one is easy to see that it's the point 0, 40. Okay, so that one's easy enough to do. This point down here is the x-intercept of the red line, and that red line is y is less than or equal to negative 2/3 x plus 134/3. So we have to figure out the value of x that makes y 0. So if we plug in 0, and we're going to subtract 134/3 from both sides, and multiply both sides by negative 3/2, this is going to give us our x value. When you do that, you're going to end up with x is equal to 67. So I know that this point here is 67, 0. And then to figure out this last point here, again, that's the point of intersection of those two inequalities. So when you set those two inequalities equal to each other and solve for x is going to end up being 10. And you plug 10 back in and you'll end up with 38. I'm not going to show you that right now. I'd like for you to try and see if you can get that on your own. Again, the two equations that are here with the arrows are the two that I want you to set equal to each other. See if you get x equals 10. I want you to go ahead and take each of those points and plug them into your function. And we're going to determine where the max and the min are. So I want you to go ahead and determine what are the f values at each of those points. Go ahead and do that calculation now. Once you have that calculation, I want you to determine what the minimum and maximum are. I'll tell you what, I'm going to let you know what the minimum is. The minimum is 0. It occurs at 0, 0. I want you to go ahead and submit. Where is the maximum? I want you to go ahead and give this problem a try. We have the Evergreen company that produces two types of printers, the inkjet and the laserjet. The company can make at most 120 printers per day and has 400 labor hours available per day. It takes 2 hours to make the inkjet and 6 hours to make the laserjet. If we know the profit on the inkjet is $80 and the profit on the laserjet is $120, find the maximum possible daily profit and the number of each type of printer that gives it. So I'm going to go ahead and get you started up, and then I want you to do the rest of the problem on your own. We know that we've got two different types of printers. I'm going to, for the sake of this problem, let I be the inkjet, and let's let L be the laserjet. I think that will help you as you go to solve this. We know the profit on the inkjet is 80 and the profit on the laserjet is 120. So we know P is equal to 80 times however many inkjets plus 120 times however many laserjets. I want to see if you can go through and figure out your constraints and solve this problem. You're going to determine the number of each type of printer that gives the maximum daily profit. Go ahead and do that problem and submit it on the screen you see to the right. So to summarize, we've done quite a few problems with linear programming. We have an objective function that will always be given, and then we have some inequalities that are given. It's the inequalities that you go ahead and graph. And you figure out what are the boundary points for those inequalities. You take those boundary points and plug them back in to that objective function. Get number values, and that will help you determine the max and the min. Go ahead now, go back and look through some of the problems that you've done. I've sprinkled some extra ones in there during the course of this video, and I'd like for you to give your homework problems a try.